Okay, so we're going to still work with the half cells that we did here, but we're going to look at what the electrical potential is of those cells. How do we figure out how much energy that a lithium ion battery, what is the voltage of a lithium ion cell? So I can figure out how many I need to operate my phone. Well, I didn't do it, but somebody did. We are going to do this looking at empirical data. Okay. So if you notice the numbers along the left side or the right-hand side of your chart in your data booklet, there's a bunch of numbers, and we're going to talk about how we got those. Or, as I should say, how they were given to us. So we are going to talk about standard cells and cell potentials. Now, what is a standard cell? It is a cell with set conditions. Okay. Because we want to talk as a group about what is the voltage for this cell, scientists have decided let's set a basic condition set that we can use for these cells to facilitate the discussion. It doesn't mean that we always create those cells at those conditions, but it allows the discussion to be made as we go over them. So a standard cell is a cell that contains all of the entities present on both sides of the reactions in a concentration of 1 mole per liter and a temperature of 25 degrees Celsius and a pressure of 100 kilopascal. So when two scientists are saying, I've discovered this great new battery, can you check and see if it works? And my findings are fine. They can say, okay, at these conditions, this is what it gave off. Shorthand notation, at standard conditions. That means you have the zinc and you have the zinc 2+ on both sides of the reaction. In this one, we have the chromium 2 and the dichromate and the hydrogen ions. That's going to be our OA, but we also have the chromium 3 that is created after they react, because they want to be able to go both ways. The carbon is our inert electrode, just where the electrons can, in this case, move into solution. Okay. So that's the inert electrode idea. Now there's some notation here. We talk about E cell. This is the standard potential energy of that cell. So at standard conditions, this cell should give me this many volts. Now, this little thing up here represents the standard conditions. And this is essentially telling us if you create these at standard conditions, you should get this reading on a voltmeter. Okay? That's what we mean by cell potential. How much voltage can this cell give us? So when we talk about a 1.5 volt battery, that particular cell or battery is giving us off 1.5 volt potential difference. Sound is set up and all that other fun stuff that I forgot to do earlier. Just changing classrooms I'm not used to. Saying classrooms that's not.
Hi, this is Dr. Hayek, and this video is about electrochemistry, and today we'll be talking about the standard reduction potential. In my last video, I have introduced a galvanic cell and how can we build one. Please check the link in the description below to see this video. Once we build a galvanic cell, the remaining question is, how can we calculate the cell potential? Before answering this question, we need to discuss the standard reduction potential of half equations. As you know, the redox reaction is the sum of two half equations, the oxidation and the reduction, and the cell potential is the potential energy of this reaction. If we can determine the standard reduction potential of each half equation, it will be easy later on to calculate the cell potential from the potential energy of the redox reaction. However, there is no way to calculate the standard reduction potential of half equations individually. Therefore, we will need a starting point and a reference. Consider the following galvanic cell where zinc is at the anode and hydrogen is at the cathode. Zinc is getting oxidized and therefore is losing electrons, and the electrons are being transferred to the hydrogen at the cathode, and hydrogen is getting reduced. As the two hydrogen ions will take two electrons to form hydrogen gas, which will escape the solution. The voltmeter is indicating a cell potential of 0.76. If we assume that the standard reduction potential of hydrogen is equal to 0, therefore the standard reduction potential of zinc is going to be equal to the negative of 0.76, and the sum of both standard reduction potential will give us the cell potential. In a similar way, we can determine the standard reduction potential of other half equations, as you can see it in the following table. So now do you know how to calculate the cell potential of this galvanic cell? Take the corresponding half equations from the table, then flip the aluminum half equation because it's an oxidation and it's happening at the anode. And when we flip the half equation, we flip the sign or we reverse the sign of the standard reduction potential. Therefore, it's negative E0 is equal to 1.66. Now, to sum these two half equations, as we know from balancing redox reaction, we need to multiply by two integers. We need to multiply by 2, the half equation of aluminum, and by 3, the half equation of lead. And a very important remark is that when you multiply the half equation by an integer, you do not touch the standard reduction potential. After that, when you find the redox reaction, you sum the two standard reduction potentials, and therefore you get the 1.53, which is the cell potential. Once a galvanic cell is built, we can describe it using what is called line notation. Now, the line notation, we started by writing the anode to the far left, the cathode to the far right, and then with two lines in the middle that will represent the salt bridge or the porous disk. Now, between the electrodes and the solution, we put two lines, and therefore, since aluminum is getting oxidized into aluminum 3+, so we put a line between aluminum and aluminum 3+, and lead is getting reduced to lead solid, and there is a line in between these two. Here is another example where a non-metal is used in a galvanic cell. We can describe this cell using the following line notation. The anode to the far left, the cathode to the far right, and then the two lines that will represent the salt bridge or the porous disk. Now zinc is getting oxidized into zinc 2+. However, here we have used an inert metal as a cathode, and therefore now we separate the solution, which is the H+, and hydrogen gas by a comma, and we write it this way. So H+ is getting reduced into H2 gas. We can also indicate the concentration and the pressure in the line notation, as you can see it in the following.
That gets a little bit.
I hope this video was helpful to you, so please like, share, and subscribe, and I'll see you next time.
Now, introduction is exactly what it is. Okay, so what he's talking, he kind of glossed over it. I'm going to show you a slightly different method that used for creating that. We're basing this on the idea of competition for electrons, which is most of electrochemistry. The cell with the greater attraction for that electron is going to be the more positive electrical potential. The half cell potential will be more positive. That still doesn't mean that we couldn't have a negative. One cell has a half cell potential of negative 0.13, another one at negative 1.35. What we're going to do, instead of flipping and changing the sign, we're just going to kind of remember a concept, because this is what it works out to be. When we basically, because we had to flip that one and then change the sign on it and just add them together. Well, flipping, changing the sign, and then adding is the same as subtracting. Okay. So we're going to take the cell potential of the cathode, subtract the cell potential of the anode. Going back to what he had there. Geez. Technology is one of those things.
The half equation will flip the sign or reverse the sign of this symbol.
So, if we look here, this is what he's done. He's identified, the lead has a stronger attraction for electrons than the aluminum does. So it's going to steal electrons from the aluminum. He writes this down with a negative 0.13. Off our table, the aluminum has a negative 1.66 volts electrical half cell potential. Well, because he flipped the reaction, he changed the sign. And now he's just going to add them. Well, it's the same thing as taking negative 0.13 minus negative 1.66. So that's where that equation comes from. It's not made up per se. It's just reducing or simplifying the process that we have here. It also makes sure that we don't have to double or triple anything. Don't forget not to double or triple like we would do in thermochemistry. Okay. Because it's based on potential energy, we cannot theoretically determine what the electrical cell potential is. We have to measure it in terms of another cell, what we set to be zero. I think of it very much like the same idea as temperature. We have Celsius and Fahrenheit and Kelvin, three normally used temperature scales. Celsius was based upon the freezing point of water and the boiling point of water. They basically took those, that's going to be my zero, the freezing point of water. The 32 degrees Celsius for Fahrenheit, he set zero to be the coldest he could get his lab to. And the highest was the temperature of the human body. So that's where the guy who created Fahrenheit, put it out there. Coldest I can get my lab to is going to be zero. Warmest, the temperature of a human body is going to be 100. Fine, it works. And we know for Kelvin, we set absolute zero to be zero, and it's going to go based upon the same scale as Celsius for life to make life easy. When we do this with this, we have to pick. They had to pick a half cell to be zero. Just like the two guys with temperature decided on two different 0 points, two different guys could have argued for two different 0 points. We have chosen, it was chosen that they chose the hydrogen half cell to be 0. Why? Excuse me. I don't know exactly why. I think it's the simplest, one of the simplest half cells, hydrogen being the simplest element. It is about halfway between the middle of the table that we use, so it's about halfway generally. And so in terms of why, that's what they chose. They could have just as easily chose lithium or fluorine. They could have chose at 0, but then we have negative signs. So it really doesn't matter what was chosen. The hydrogen half cell looks exactly like this. We take gas, at hydrogen gas at SATP, bubble it into a solution, 1 mole per liter acidic solution, where we have hydrogen ions, and just a platinum electrode. What we do from there to get every other half cell is we connect this particular cell to the cell and read the voltmeter. That's why that table that we have here is based upon all these numbers on the side are based upon empirical data. So the voltmeter, or the half cell potential for zinc, is negative 0.76. So they created a zinc half cell, connected to a hydrogen half cell at standard conditions, connected a voltmeter to it, read it, and found that the electrons were flowing towards the hydrogen. So the 0.76 came off the voltmeter. The negative that is assigned to zinc comes from the fact that it is giving up electrons to the hydrogen half cell. So it has a lower force, a lower attraction for electrons. So we're going to assign that negative 0.76. Did it go down the wrong way? Funny that. Either that or it's vodka. You think it? I've seen it. I've actually been in a classroom.
Yeah, right before I get
Well, right before your mother beats you upside the head with her shoe or something. Okay. Now, setting the hydrogen half cell as 0 was, as I said, purely arbitrary. It could have been anything. However, that doesn't change what the voltmeter would read back here. Okay. Just purely arbitrary, it doesn't matter. This voltmeter reader is going to be the same if this is set at 0 or this particular one is set at 0. Okay. So if we had set it differently, we would have given zinc a positive 0.7 volt if we had set the water half cell as 0. Okay. If we'd set the lithium half cell as 0, it would have been a different reading. But the connections between the volt, when you connect the cells, you'll always have the same value. Okay. The half cells will be different, but when you connect them together, they're always going to be different by that same amount. Okay, we already talked about that. I don't know how much I read. And there's just the idea again. These would be, okay, we set hydrogen to be 0. We set zinc to be negative 0.76. So the difference is negative, or is 0.76. If I had set the lithium half cell to be 0, then the hydrogen half cell would be positive 0.304. Lithium being way at the bottom, the last one on our table. The zinc would be assigned a 2.28 volts, but the difference between them is still 0.76. So these numbers here could change. I could shift them up or down, but the cell potentials would always be the same. Okay, so we are going to take a standard dichromate lead cell, and we're going to do exactly what we did earlier today. So I'll quickly speed through that and then deal with the rest of it. The cell notation. Oops. Dichromate lead. Okay, so now, again, I got that off of my remembering of my data book. These are all the things in the lead part. These are all the entities, except for water, in the dichromate reaction. Now, because we're talking at standard conditions, these guys are all 1 mole per liter, and we're at 25 degrees Celsius and 100 kilopascal. That's my SOA. That's my SRA. Now, because I'm only asking for the cathode and anode, I don't need to write the net cell reaction, and I can answer the rest of the questions from here. The electrons flow in that direction. The anions flow that way. Cations flow in that direction. I know I kind of shoved it in there, and I'm sorry about that. Now, before we do the cell potential, what can we see? Okay. In our anode, our lead is losing mass because we're using it up. So that's, again, one entity that you can see. There's no solid at the cathode, so no mass change at the cathode. The dichromate is orange, though. So the orange thing that creates the orange color is being used up. So you're going to have a less intense orange at the anode, or sorry, at the cathode. And then we have the hydrogen ions being used up also. So less acidic, higher pH. We always make a mistake on that. And we catch you at least 5% on the time on the diploma with that mistake. Because I've seen that question multiple times. pH gets lower. No, the acidity gets lower, the pH gets higher. Okay? So, basically what we did earlier in the day. The cell potential. We want to know what a voltmeter connected to this would read. And that is going to be the half cell potential. Now, do you remember which one goes first, anode or cathode? Cathode. Because we flipped this guy, we would change the sign. So we're going to, if we were doing this here, we don't change the sign overall. We have the cathode minus the half cell potential for the anode. I do not remember what that is. Dichromate is positive 1.23 volts. The lead cell is negative 0.13 volts. So again, all I'm doing is reading the numbers along the side. Did everybody find those? So a voltmeter connected to this would read, to this cell, would read 1.36 volts with the electrons flowing towards the carbon electrode, which is your cathode. I'm going to be nice. I'm not going to assign any homework today. I am going to assign a bit of reading. So your reading would be page 612 to yep. To 636. Yeah, it's a lot, but there's sections with questions, etc. So 612 to 636 for Monday. I will finish off this lesson Monday and assign those questions at that time. I hope you guys do not have big plans to gather in places where people are also. You're doing what? Garden? Or you do me here? Be careful. I'm not reading much like that. Next week's volleyball is again. For now, I'm hoping to make a decision each going next week. It is dependent upon what we have. If you know the contact better than I, right? I know that these two people are in isolation right now. So basically the grade 11. Well, actually, pardon, most of it. Because Maria isn't here.
I didn't hear you.
And then I know.
It was like the.
Oh. Grade 11 already got the junior boy, the junior team went to. Or at least part of it.
Especially on the team.
Yes. It is not.
Yeah,